Welcome back. We're going to continue our discussion on electron pair geometry, but before that I would like to um, bring this table in. Okay. Okay. As we work our molecules. Now if you see what we will see in the next week's video, which is week 5, we will talk about molecular geometry, and if you've noticed, there will be a slight difference in how we construct molecules, for how we name them based on an electron geometry versus a molecular geometry. Okay, for an electron geometry we treat the lone pairs, which we will see in the next few examples, as bonds. Okay, so what I'm saying here is, let's take the molecule ClF3. Okay, now we know chlorine is in 7A, right? So it's got 7 valence electron. Okay, fluorine is also in 7A, so each fluorine has 7 valence electron, right? So as I said, the element that's least in count goes at the center, so I'm going to put my chlorine at the center, and it's got 7 electrons, so I'm going to try my best to spread them around. So I think I have my 7 now, right? Like I said, if you're slightly off, you can complete the circle with 7 electrons, that's okay. Don't get bogged down with these cosmetic things, because everything we're doing here is very abstract. Okay, so if there's a little skew in your sketch, it's not going to affect your understanding of the content. Okay, now I'm going to switch colors here, and each fluorine has got 7 electrons, right? But keep in mind, for the outer electrons, I think when it's more than 2, we should try to split them into pairs of 2. So we got 7. So if I split 7 electrons into pairs of 2, I'm left with 3 pairs of 2 and an odd electron, right? That's how I end up with, right? So I'm gonna go, I have 3 of these, right? Because keep in mind, I've got 3 fluorines, right? So I'm gonna, it really doesn't matter where you position them. I'm just gonna position them just where I want them to be. So I'm gonna put them all over here. Okay. Okay, now get your bonds. Let's get a different color, perhaps a red. Okay, and then connect the blue and the black, blue and the black, blue and the black. Remember, a bond is made up of 2 electrons. Now if you notice quickly that there's 2 pairs of electrons, right? These 2 pairs of electrons are what we call the lone pairs, right? Now the molecule, whether it's polar or non-polar, is much more, is definitely made simple by the presence of these lone pairs. And as I said, the atom in the central is given A. There's only 1. There's 3 outer atoms, so there's 3x, and there's 2 lone pairs, so it's E2, right? Right away I told you a molecule with a lone pair rarely turns out to be non-polar. So we know this molecule is polar. Okay, and so that's this just tells you about the polar, right? Now if you draw out the molecule, right, you've got, it really doesn't matter how you draw it out. You know, I'm just drawing it out. I got 2 lone pairs, right? Right, it really doesn't matter how you draw it out. So when you go, and when we talk about molecular geometry, this will be a slightly different geometry. But looking at this right here, it's AX3E2, right? Which is trigonal bipyramidal. Because for molecular geometry, we treat the lone pairs, we don't treat the lone pairs as bonds, whereas for an electron pair geometry, we treat the lone pairs as bonds themselves. Okay, so that is trigonal bipyramidal, right? Very good. So it's AX3E2. remember this molecule, because we're going to come back to this when we do molecular geometry, is we're going to resurface this molecule one more time just to see how they are slightly different. But the key here is this molecule is 5 bonds, right? Because we are treating the lone pair as a bond. So this molecule technically is same as a AX5. Okay? It is as if it behaves like, it is as if the AX3E2 behaves like a trigonal bipyramidal. Okay, so working electron pair geometry is much easier than molecular geometry, because the names, as long as you have 4 bonds, are equivalent of 4 bonds including the lone pairs, is tetrahedral. If it is 3, it's trigonal planar. If it's 2, it's linear. If it is 6, it's octahedral. If it's 5, it's trigonal bipyramidal. So no matter how many E's you have, if the total bond counts add up to 5, then it is going to be trigonal bipyramidal. So it's much easier to work with electron pair geometry over a molecular geometry. Okay, so let me come back, and I'm going to delete this and bring back my geometry table. Let's just pick a different molecule this time around. Let's say we do XeF4. Okay, right? So xenon, okay, it's in 8A, right? 8A. So it's got 8 valence electrons, right? And fluorine is in 7A. So it's got 7 valence electron for each of the fluorine, right? So we put the element that's low in count at the center. We got 8, so let's go ahead and 5, 6, 7, 8, right? And we got 4 fluorine, so let's go get a different color. So fluorine, each fluorine, I'm just gonna get straight to the chase because you've seen enough of it. It's got 7, so I'm gonna just position them in such a way that they are around each of the dots on the xenon. Okay, and then so now get a different color and connect the bonds. Blue and black, blue and black, sorry, red and black, red and black, right? Now we're left with 2 lone pair of electrons, right? A lone pair, a pair is made up of 2, right? So the formula here is AX4E2, right? But this is electron pair geometry, right? So we treat the lone pair as electron pair geometry. So we treat the lone pair as bonds. So technically there are 6 bonds, so it has to be octahedral, right? And whether the molecule is polar or not has to do with whether it contains a lone pair. If it contains a lone pair, what it's really doing is, between xenon and fluorine, if you remember, okay, we don't really have electronegativity value for xenon, but we're gonna assume, because no value is very little value, so I'm gonna get my pink color here. Okay, because this is of no value, we're gonna treat this as very little electronegativity, and so that's gonna get the positive, right? And then same for all of them, right? It seems like it's an umbrella, right? It seems like the lone pair is like an umbrella which is sitting here, okay, pushing all the spokes down, so you have a net polarity that acts only one way down. Okay, now again, I'm just explaining this. You don't have to really show me all this umbrella effect and stuff like that. Okay, I just did that. So what the lone pair does is it pushes all the arrows, you know, one way downwards, like an umbrella pushing, you know, like all the spokes down. All the spokes are facing down when you open an umbrella. That's kind of what happens. So based on that, we can say that this molecule is polar. Okay, so I'm going to do a couple more examples just to get the point across.